This video will deal with solutions to section 5.10. Section 5.10 is improper integrals. I'll start with number 16. The instructions state, determine whether each integral is convergent or divergent. Evaluate those that converge. And number 16 is the integral from negative infinity to infinity of cosine pi t dt. So this is an improper integral, so we have to rewrite this. It goes from negative infinity to infinity. So we're going to have to rewrite this as two limits. So we're going to have the limit as t approaches negative infinity. The integral from t to, we can pick any number we want here. I'll just choose 0. Cosine pi t dt plus the limit. And we can use t here, we can use another letter. I'll use b just so we're not confused. The limit is b goes to infinity. The integral from 0 to b of cosine pi t dt. Okay, so it's an improper integral. We have to break it up into two limits. The fundamental theorem of calculus does not allow us to evaluate an integral if one of the bounds is infinity. It has to be, in this case, t and 0, it's got to be a value, a number. So we can get around that by putting a t here and then taking the limit after we evaluate the integral as t, in this case, goes to negative infinity. Over here, we're doing b as b goes to infinity. This is a u sub, right? U is going to equal pi times t. So du is going to be pi dt. So we can rewrite this as the limit as t approaches negative infinity. We're going to need a 1 over pi outside. This is going to be cosine u. And remember, we multiplied by pi right here that to get our pi dt on our u sub. That's why we have the 1 over pi, the reciprocal out here to balance that. So this would be cosine of u du. No bounds on the integral because it's a definite integral, but we're doing a u sub, so there are no bounds here because t and 0, those are values of t. Now I just noticed that I'm doing this with t here and t here, and we have a t as our variable of integration. So I'm going to change this. We're using b over here. Over here we'll just use c. Okay. There we go. Over here, then we're going to have plus the limit as b approaches infinity. This will be the integral, no bounds, because this is the same u sub. So this will be cosine of u du. And we still need our 1 over pi from our u substitution. When we integrate cosine, we get sine. So this becomes the limit as c approaches negative infinity. 1 over pi sine of u is pi t. We're going to evaluate that now because we're back into t, our variable of integration, between c and 0. Plus here, we're going to have the limit as b approaches infinity. We're going to have our constant 1 over pi. The integral of cosine, of course, is still sine, just like it was here. So that's going to be sine pi t. And we're going to evaluate that between, in this case, 0 and b. Now, everybody has a 1 over pi, so we can just factor a 1 over pi out in front. Here, we're going to have the limit as c goes to negative infinity, sine, well, I'm sorry, did my fundamental theorem of calculus backwards. So we're going to plug in 0. Sine of pi times 0 is sine of 0. That's going to be 0. Minus we're going to plug in c, and so we're going to have sine. We're going to have the limit as c goes to negative infinity. And then we're going to have c times pi, or pi times c. Plus here, our upper bound is b. B is going to infinity. So this would be the limit as b goes to infinity. We've got our 1 over pi out front. So this would be the sine of pi times b minus, and then we plug in our lower bound of 0. 0 times pi is 0. Sine of 0 is 0. So when we take the limit here, somebody forgot to write down the sign here. When we take the limit here, what do we have? We have 1 over pi. When we take the limit, we have the sine of negative infinity plus, because negative infinity times pi is negative infinity. Infinity times pi is infinity. And this is what we end up with. Well, we cannot evaluate sine of negative infinity, or sine of infinity for that matter. The graph of sine oscillates on a regular pattern as our angle goes to infinity, as x goes to infinity. We don't know where this is. We know it's bounded above by 1, and we know it's bounded below by -1, but we have no idea where that value is. So this cannot be evaluated for the same by the same argument. On this side, this is oscillating as well. This cannot be evaluated. So this integral diverges. Okay, so that's the answer to 16. I'll pause the video, erase the whiteboard, and be right back with you. The next problem I'll work on is number 19. 19 is the integral from 1 to infinity of the natural log of x divided by x dx. Another improper integral. We'll have to rewrite this as the limit as t approaches infinity, the integral from 1 to t, ln of x over x dx. This is a u substitution as well. We're going to let u equal the natural log of x. The derivative of that is going to be 1 over x, which we have, dx. So this integral is going to be the limit as t approaches infinity, the integral, no bounds because we're going to do a u substitution. The natural log of x is u. 1 over x, which is what we have right here, dx, that's du. So we end up with the integral of u du. This gives us the limit as t approaches infinity. The integral of that is, of course, going to be u squared over 2. Now, when we plug back in our value of u, we're going to get the limit as t approaches infinity. We're going to have the natural log of x squared divided by 2, evaluated between 1 and t. If we plug in t, we're going to have the limit as t approaches infinity, and we're going to have the natural log of t squared over 2 minus, and when we plug in 1, the natural log of 1 is 0. So we get 0 squared divided by 2, that's going to be 0, and so this is our limit. Well, as t goes to infinity, the graph of the natural log looks like this. It's increasing. It's strictly increasing, right? It's monotonic. It increases as we go to the right. So as t goes to infinity, the natural log of t goes to infinity. So this is infinity squared over 2. That means that this integral diverges. Remember, if we can't get a finite answer, then the integral diverges. Okay? Again, I'll pause this, erase, and be right back with you. Next, I'll work on problem 26. Problem 26 is the integral from 2 to 3 of 1 over 3 minus x to the 1/2, or 1 over the square root of 3 minus x dx. Now that function is undefined at 3, right? If we put a 3 into that function, which is our upper bound, we're going to have 3 minus 3, that's 0. The square root of 0 is 0. 1 divided by 0 is undefined. So this is an improper integral. It doesn't have an infinity in its bound, but the function has a vertical asymptote at 3. So we have to rewrite this as the limit as t approaches 3 from below, right? Because we're going from 2 to 3. So here's our number line. Here's 2, here's 3. We're integrating this, so we're going from 2 to 3, so we're approaching 3 from below. The integral from 2 to t, 1 over the square root of 3 minus x dx. It's another u sub. We're going to let u equal 3 minus x. du is going to be minus, right, the derivative of this, minus dx. So we need a negative sign here, which means we need a negative sign out front. So now we have minus, putting the negative all the way out front, the limit as t approaches 3 from below. The integral, no bounds, because we're doing a u sub, no bounds. And this is going to be 1 over u to the 1/2, right? 1 over u to the 1/2 is u to the minus 1/2 du. Right? Because we have 1 over u to the 1/2, because what we really have is, I guess, 1 over the square root of u. So that's u to the minus 1/2. So when we integrate that, we're going to get minus. We still have our limit. The integral of this, we add 1 and divide, right? We add 1 and divide. So u to the negative 1/2 plus 1 is going to be u to the positive 1/2. We divide by a half, which is the same as multiplying by 2, right? Dividing by a half, we multiply by the reciprocal. And so now when we plug back in our value for u, we can put the 2, that's a constant, so we can put that out in front. We have the limit as t approaches 3 from below, and we have u to the 1/2. So we have here the square root of 3 minus x, because that's u. And we're going to evaluate that between 2 and t. Now, there's our negative 2. Here's our limit as t approaches negative 3. When we put a t in here, we get the square root of 3 minus t. Over here, when we put a 2 in here, right, we got to put our lower bound in. 3 minus 2 is 1. We get the square root of 1. Now, when we put a negative 3 in here, we get 0, right? When we take the limit of this as t goes to negative 3, this becomes, hold on just a sec. It's not supposed to be negative 3. That's right. Suddenly my brain was like, how did you get a negative 3 there? I didn't. It's supposed to be 3 from below. So we put 3 into here. 3 minus 3 is 0. Square root of 0 is 0. So we've got our negative 2 here. We have our 0 when we evaluate our limit, minus 1. And so negative 2 times negative 1 gives us an answer of 2. So this one converged, and the value of the integral was 2. Well, that's nice that one of them converged since the previous 2 diverged. All right, so I'll erase this, and I'll be right back with you with one more problem from this section. All right, for the last problem that I'll do in this section, I'm going to work on problem 44. Now, problem 44 says, use the comparison theorem to determine if the integral, and in this case, it's integral from 1 to infinity of 2 plus e to the minus x divided by x dx converges or diverges. Now, the comparison theorem requires a little bit of analysis on our part, right? We know this integral may converge, it may diverge. We also know that we don't know how to integrate it, right? This integrand that we have here, we can't integrate this. Nothing works. You can't do a u sub. Partial fractions doesn't work. It doesn't fit the format. It's not a polynomial divided by a polynomial. It's not a trig sub. There's no a squared minus or plus x squared or x squared minus a squared here. It's not a trig integral. It doesn't have powers of sines and cosines or powers of tangents and secants. And it's certainly not parts. So the comparison theorem says, when faced with an integral like this, one of the techniques that you can use is you can find a function that's similar to your function. See, our function is 2 plus e to the minus x over x. We're going to infinity. Now, the graph of e to the minus x, right? If we put a 0, we're just going to look at this. We know what 2 and x look like as x grows with that bound. What about e to the minus x? Well, when we put 0 in here, we get 1. When we put 1 in here, we get 1 over e, right? When we put 2 in here, we get 1 over e squared. When we put 3 in here, we get 1 over e to the third. This function is getting smaller and smaller and smaller. But now I only graphed it from 1 over because our lower bound is 1. So what can I conclude from this picture? Well, I can conclude this. E to the minus x is always positive for all x greater than or equal to 1. It's always going to be a positive number. Now, how is that significant to me? Well, remember, our goal here is to find something to compare our function to. And we want to find something that's relatively simple, first of all, because we have to be able to integrate it, and something that we can analyze and compare to our function. If we consider the function 2 divided by x, what can we say about this function relative to this function? Well, e to the minus x is a positive number. It may not be very big, but it's a positive number. And if this numerator is bigger than this numerator, which it is because e to the minus x is positive, so 2 plus something is going to be bigger than 2, because that something is positive. The denominator is the same thing. So we can say that this function is greater than or equal to this function for all x greater than or equal to 1. Now, how does that help me, you may ask? Well, it helps me this way. I can integrate this from 1 to infinity. Now, what happens then if I take this integral and I write it here? I can't find it, right? I don't know how to integrate that. This integral, however, I can find. And my integral is bigger than that integral on the right. Well, the comparison theorem says, okay, in this case, if this is infinity, then you're greater than or equal to infinity. If this diverges, your integral is greater than or equal to this integral. Therefore, if the one on the right diverges and you're bigger than that, you also must diverge. That's how the comparison theorem works. You can also argue the other way and talk about convergence, right? If your integral is smaller and it converges, then, if your integral is bigger and it converges, then the smaller one must converge. So we're going to evaluate this integral right here. We're going to take that integral. We're going to rewrite this as the limit as t, because it's an improper integral. We can integrate 2 over x. We know that's the natural log of x. So this becomes the limit as t approaches infinity, the 2 times the natural log of the absolute value of x evaluated between 1 and t. that becomes 2 because the constant can come out. The limit as t goes to infinity, the natural log of the absolute value of t minus the natural log of 1. Now that's 0. So the limit as t goes to infinity, the natural log, the graph of the natural log, right? The graph of the natural log, we know that graph. The graph of the natural log goes like this. It grows without bound. As t goes to infinity, our graph goes to infinity. So this diverges, right? But our integral, by our comparison theorem idea over here, our integral is larger, right? Greater than or equal to. So if this integral, which is smaller than ours, diverges, then our integral, which is bigger than that by our work here that we did, it must diverge. That's the power of the comparison theorem. We should spell that right. Okay, that concludes my video on section 5.10, improper intervals.